Introduction. The discovery and understanding of the atom's structure have revolutionized our comprehension of matter. Throughout history, scientists have explored and refined the atomic model, enabling us to grasp how the atom's fundamental components influence chemical behavior and the properties of the surrounding matter. Simplified timeline of atomic models. In 5th century BCE, Democritus proposed that all matter is composed of tiny, indivisible particles called atoms. In 1803, John Dalton proposed that elements are composed of indivisible atoms. Atoms of the same element are identical, and compounds are formed by combinations of atoms in fixed ratios. In 1897, J.J. Thomson discovered the electron and proposed the plum pudding model, where electrons are embedded in a positively charged sphere like plums in a pudding. In 1911, Ernest Rutherford's gold foil experiment led to the discovery of the nucleus and proposed the nuclear model, where atoms have a small, dense, positively charged nucleus orbited by electrons. In 1913, Niels Bohr expanded upon Rutherford's model by incorporating the quantization of electron orbits, suggesting that electrons orbit the nucleus in fixed energy levels or shells. Modern understanding of the atom is based on quantum mechanics, which describes electrons not as particles orbiting the nucleus, but as waves or probability clouds. This model provides a mathematical description of the behavior of electrons in atoms. These are the key milestones in the development of atomic models, each building upon the previous one and leading to our current understanding of the atom. Importance. The role of atomic structure in chemical reactions and energy technologies drives innovation across various scientific disciplines. The atom's structure shapes the behavior of matter, underpinning current chemistry, physics, and technology. Understanding atomic structure unlocks perspectives on matter's properties, propelling scientific advancements. What is an atom? The atom is the fundamental unit of matter. It consists of a central nucleus containing positively charged protons and neutral neutrons, surrounded by a cloud of negatively charged electrons. The interaction between these particles determines the properties and behavior of chemical elements. What are its components? Electron cloud. Region around the nucleus where electrons orbit. Atomic orbitals. Three-dimensional regions where electrons are most likely to be found in an atom. Electron. Negatively charged subatomic particle orbiting the nucleus. Neutron. Neutral particle in the atomic nucleus alongside protons. Atomic nucleus. Positively charged center of the atom containing protons and neutrons. Proton. Positively charged particle in the atomic nucleus. Particle-to-mass relationship. Mass comparison. The proton-electron mass ratio, PEMR, indicates that protons and neutrons are much more massive than electrons in an atom. Impact on atomic mass. The electron's mass is negligible compared to that of protons and neutrons, predominantly determining atomic mass. Effect on chemical properties. PEMR influences chemical properties by affecting electron attraction to the nucleus, thereby influencing reactivity and chemical bonding. What is electron configuration? The arrangement of electrons orbiting the nucleus is referred to as electronic configuration. The electronic configuration dictates how an atom interacts with others, influencing its ability to form chemical bonds and engage in reactions. This understanding is crucial for explaining the properties and behaviors of elements in the periodic table. Electrons in an atom do not orbit the nucleus in the classical sense. Rather, they are found in regions of space called orbitals, which are characterized by the probability of finding an electron at a particular location. These orbitals are organized into energy levels, often referred to as shells, which are labeled with the letters K, L, M, and so on. Each shell can contain one or more subshells, which are further divided into orbitals. The first shell, K, consists of only one subshell, which is the s subshell. This s subshell can hold a maximum of 2 electrons. The second shell, L, contains 2 subshells, the s subshell and the p subshell. Together, these subshells can hold up to 8 electrons. The third shell, M, includes 3 subshells, the s, p, and d subshells. The maximum number of electrons that can be accommodated in these subshells is 18. The fourth shell, N, encompasses 4 subshells, S, P, D, and F. These subshells can collectively hold a maximum of 32 electrons. These shells and subshells are defined by the principal quantum number, N, which indicates the energy level of the electrons within the atom. The number of electrons that can occupy each subshell is determined by the specific quantum numbers associated with that subshell. In conclusion, the structure of the atom, understood through its components and their relationships, along with electronic configuration, forms the foundation of our understanding of chemistry. This knowledge has enabled us to unravel the secrets of matter and create technologies that enhance our lives.